Well, my second lecture this morning is also based in part on the Royal Society of Edinburgh conference. This time it was the second conference. It was a conference on the science of beauty. I'm going to be showing the video of that, but it'll be truncated, shortened a bit, so it'll start rather abruptly, and then it'll come in two parts. There'll be a small bit at the end, but most of it will be at the beginning. And because it's a little longer, this second lecture will last a little longer. It'll go on until 12:45, including question time. And I shall be adding, as before, a lot of material in the form of slides, which substantially adds to what's in the video text. It is related to the first lecture, but it's more philosophical and it deals with broader issues. And as I say, at the end we'll have an open discussion with some questions from the audience, which will be recorded as well. Okay, enjoy the lectures. Now, my first picture is one which is meant to illustrate beauty in mathematics through geometry. And so the most beautiful figure in geometry is starting off with is the equilateral triangle. I hope you all know what an equilateral triangle is. And then I've also doubled it up. I've taken its mirror image, or if you imagine it spinning around an axis, you'll get a second copy. And so those are the two fundamental equilateral triangles, which play a very important role in all sorts of fields, mathematics and art and so on. So now let us move on to something a little bit more interesting. You all know what the equilateral triangle is, but you may not. Well, I hope you all know what the next one is. If I press the right button, let's try this one. Ah, yes. Now you may not recognize this one immediately, but a little reflection will tell you from the tetrahedron, by the way. You start with the tetrahedron, which is the simplest thing after a triangle in 3 dimensions. And from a tetrahedron, with a wave of the hand, you can construct two beautiful objects, the icosahedron and its dual, the dodecahedron. If you haven't done it before, go back home and get your children to help you construct one. And you will find that automatically, from a tetrahedron, you can manufacture both the icosahedron and the dodecahedron. Now, that may be a great discovery for you, elderly people. The youngsters may have known it at school, but in fact, it's been known for millennia, because it was first discovered by the modest virus. Most viruses are in the form of an icosahedron, if you didn't know, and there's a good reason for that, because it's the simplest thing you can do by doubling up. You start with the tetrahedron, you wave a magic wand, and lo and behold, you get the icosahedron and the dodecahedron. So the virus, which we all have, we wouldn't be here without viruses, because the virus is also related to DNA, and the viruses come in two forms, one more like the icosahedron, which here the icosahedron is shown with jagged edges. There are lots of nice vertices, and those are what you might call the sharp end of the virus, which is what a virus uses to deter attackers. And then there's the other one, there's the round one, which is more like the picture of the dodecahedron, which we'll see shortly, and that one is the one that is used to get away. The most important things in life, whatever you are, whether you're a football player or a virus, is to deter attackers and run away when necessary. So, now those are deep thoughts. Now, on the other hand, you will see the tetrahedra, if you look inside there, you will see, well, you'll see 5 colors, won't you? I hope the picture is right. You've got 5 colors, and you've got 4 tetrahedra. And 4 times 5, or 5 times 4, if you prefer, is 20. And I hope even the oldest people still learn their multiplication tables, and will remember that, because it's a very important fact that those add up to 20. Now let me go to the dual picture, which is the picture of the dodecahedron. Now the dodecahedron, as you can see, has 4 colors. I hope I'm right. And they curve 5 times. And 4 times 5 is 20. But that wasn't the same as that one before, which was 5 times 4. And, you know, the most important rule you learn in arithmetic at school is that 4 times 5 is 5 times 4. But there's some subtlety there. Now, let us talk a bit more about the dodecahedron and the icosahedron. Now, the history of these things is quite interesting. And history has a lot to do with football. You know that if you take a icosahedron and truncate it, you chop off the edges, the vertices, you will end up with something which is made up out of pentagons and hexagons, which is in fact the modern football. So now let us go on to the question of colouring. You notice these pictures were coloured, and I referred to the fact that one of them had 4 colours and one of them had 5 colours, and you've got to remember that. It's very important. Now, the most important thing to remember is there is a simple rule for finding 4 colours. It goes back to lots of fundamental bits of algebra in the past. It's related to the fact that you can solve equations of degree 4, written down there, but there is no corresponding rule for choosing 1 out of 5. If I give you 5 things and you ask you to choose one, you can't do it. At least you can't do it by the usual rules of either using ruler and compass, or equivalently using only things like square roots and cube roots and fifth roots. It's not possible. And that will come back one of the most famous theorems in history of mathematics. So there are theorems of algebra about equation 4, but 5 is where the story really starts. So let me go on to 5. Now the quintic equation, if you're not good at Latin, I'll tell you quintic means 5, and equations of degree 5 or more cannot be solved using only square roots, cube roots, and fifth roots, or any other roots you like. Now that took mathematicians hundreds of years to find out, painfully. They tried. It took them a long time. Well, everybody knows how to solve quadratic equations. You learn that, well, you used to learn that in some studied in school. Some of you may even remember the formula. And with a lot more work, and over another century or two, people worked out how to solve cubic equations. And with even more work, and more hard work, finally they worked out how to solve equations of degree 4, and that was a famous landmark in mathematics, and then they got stuck. They couldn't do 5. They tried hard, they tried harder still, nobody succeeded, till finally 2 of the most famous figures in mathematics appeared on the scene. Their pictures are there, Niels Abel and Évariste Galois. Abel was Norwegian, Galois was French. As you see, their dates are slightly staggered. Abel came first, Galois came second. You will notice also from their dates that they died extremely young. Galois, in fact, died in a duel. He was a radical, imprisoned in jail for radical views, and he was, the next morning, he was to take part in a duel in which he was killed, but that's well known to have been an assassination plot. They covered it up. He was actually murdered by the secret police because of his radical opinions, not an unknown situation even these days. But the last night he had in jail, he suspected something was going to happen to him tomorrow, next day. He stayed up all night, scribbling away his notes, which form the foundations of modern mathematical theory, the theory of groups. So it's a very romantic story. Abel was not quite so romantic. He just died of tuberculosis before he could get his first job. But he became an iconic figure in Norwegian history, and Norway celebrates every year. And so these 2 figures are the pioneers of modern mathematics. All that we do nowadays rests on their pioneering work. And but you needn't get depressed if you're, looking to a future in mathematics. You don't need to die young to become famous. Newton lived to be 82, Gauss lived to be 84, so you can be famous, do mathematics, and live a long time. It's not necessary to die early. But sometimes it helps your romantic future. You get iconic status, and these 2 figures are, without doubt, the 2 most romantic figures in history of mathematics. We all dote on them. The French dote on Galois, the Norwegians dote on Abel. We all admire both of them. And they showed, what's written at the bottom of that slide, that an equation of degree 5 cannot be solved by using square roots, but you have to solve it by using some more complicated functions than just square roots. You have to solve by using elliptic functions. Now, elliptic functions, as the name suggests, have something to do with an ellipse. And if you go back to elementary calculus you may have done, and you find formulas for the length of the arc of an ellipse, that's using elliptic functions come from that term. So the trigonometric functions come from a circle, And the elliptic functions come from ellipses. Very simple story to remember. And if you didn't know before, you've learnt it now. Now, the pentagon. The pentagon is a very important step forward because we've seen that quintic equations are the equations that cannot be solved by elementary methods. You have to use advanced methods. Now, here is a picture of some pentagons. The one on the left is designed to show a regular pentagon, and what you see there is the blue lines which form an outside pentagon. Then we go, so those are got by starting at one point and taking one step at a time, the right number of angles, and after 5 steps you go back where you started. Supposing you take 2 steps at a time, that's the yellow line. You go around that 5 times, and lo and behold, what have you got in the middle? You've got another pentagon. So instead of solving the problem about the pentagon, you've got yourself another pentagon. And if you did it again, you keep going, and you never get anywhere. The pentagon will keep recurring. You're trying to solve a problem, and you find you've got back to the same one before. That's why you can't solve the equations. It's as simple as that. If you try it with the square triangles, it doesn't happen. So this central pentagon only appears at 5. And we'll come back to that in a moment. You'll see it in many forms. Notice that there are several circles you can draw in this picture. There is the circle round the outside, which goes through the vertices, and then there is a smaller circle inside, which I haven't drawn either, which touches the vertices. There are 2 circles, one circumscribing, one inscribed to the pentagon. I hope you can understand that, even if I don't draw it for you. Now, on the right-hand side, there is another famous pentagon. It is the headquarters of the US agencies, well known, referred to as the Pentagon. Now, if you look up in the learned works called the Wikipedia, you will find a story there that says that the origin of that pentagon has something to do with the fact that the field on which the pentagon was built was pentagon in shape, and so they called it after the field. But we know better than to believe stories coming out of the Pentagon. And I don't think you should give much credulity to that, even if it comes out of Wikipedia. These things can be planted, as you know. Now, it's much more likely that this pentagon has something to do with the fact that the pentagon was a symbol of magicians. The magic circles are usually called, well, the Pentacle Club is the club of magicians. It's a very long history. It's associated with all sorts of mystical things in the past. The pentagon was a kind of universal symbol of mystery, and so it's not coincidental, I think, that the US defense agencies hide behind that symbol. I mean, I may be being bugged here. I'm sure I'm being bugged, and I may end up there, but I hope I haven't divulged a secret. But say, don't believe what's written in the Wikipedia necessarily. Well, so now I've told you about the Pentagon. Now, after the Pentagon, we can start drawing more complicated pictures. That was 5. Even numbers and odd numbers are a bit different, so let's stick to odd numbers. The next odd number after 5, somebody remember? I think it's 7. Not quite sure. Let's see. 7. Now, you may not know that heptagon, it comes from the appropriate classical language, means 7-sided figure. So here is now 7-sided figures I can't draw by hand. I did a rough sketch, but my friends with computer graphics did a much better picture, and here is the computer graphic version, very accurately. So we have here on the outside 7 points. They form the vertices of a 7-sided regular figure called the heptagon. Then, if you now, that's going one step at a time, starting with the yellow dot and going to the other ones. But now let's say go 2 steps at a time. Now this time you follow the yellow lines. The yellow lines goes round and round and round and round and round, and it comes back again because 2 is prime of 7, and so you get back another lot of figure. And now you can see, I didn't draw it because it would be too complicated, but you can see other circles. You can see a circle that touches all those yellow lines. You could also draw a circle that goes through some vertices, then life gets really complicated, so I won't bore you with them, but you can imagine drawing, and the red dot in the middle will be the center of all of these. They will be concentric circles, and for the heptagon, you will find the outside circle, and you will find the two other ones. For the case of the pentagon, we had one inside, big pentagon and a small pentagon, here you'll find 3. And that number keeps going up. If you went up to the next level, you'd go up corresponding. You can guess the formula. You work it out, it's simple. You'll find all these nested circles, and that blue dot I think you could ignore. It's a question of which one I want to look at. Do I want to look at the circle that circumscribes or that inscribes? But they're both there. If you do them all, the picture will get very complicated. I leave that to your imagination, and imagination is a very important part of mathematics. I hope you all possess a little bit of imagination. So think of that. Now this story, let's sit back a moment. I've got plenty of time because I think I'm ahead of schedule. My chairman will tell me when I'm running out, my chairperson. If you imagine starting to do this when you replace the number 7 by your favorite big number. Well, let's say something of the order of 10 to the power 20, would that do? Well, that's a big number, isn't it? And I repeat that with that number of, well, what happens? Well, clearly going around in very small steps. The outside pentagon is almost a circle. It's a circle. It's a pentagon with so many steps that with the naked eye you won't spot the difference. But with a magnification glass, suitable power, you will see that it breaks up into very, very small segments. And then there are 2 circles, remember, there's the outside circle and the inside circle. Well, they're so close together, with the naked eye you won't tell the difference. But with very powerful magnification, you will see that they are very slightly separated, and the pentagon, the 20 million side, whatever it is, big side figure, sits in between them. Now that was the way Archimedes calculated pi. He drew large numbers of polygons with regular sides. He couldn't draw 10 to the 20, he only had limited powers, but he got up quite a long way, and every time he got up, he found 2 circles containing between pentagons. Anyway, that way around, he calculated pi to a very large number of figures of accuracy, and if he'd gone on and on, he would have got more and more accurate. Whatever accuracy you demanded, Archimedes would have got there. And he knew that. He had limited powers, but he knew essentially that he got what we call now the infinite decimal formula for pi. Not bad for somebody who lived that far back in time. Archimedes was one of the great geniuses. Everybody recognizes him as probably maybe the greatest mathematician of all time. And he discovered that how to calculate pi by drawing these pentagons and sectors. But in fact, that is also the basis of modern coding theory. If you tell somebody there's a pentagon of 7 sides, well, they can check it by hand quite quickly. But if you tell them there's a pentagon of 20 million sides, well, even if you don't tell them how many sides it has, they'll have a hard time finding it. That's the basis, really, of what's called open key cryptography. You send a message out, and if the person at the other end doesn't know what the number is, that doesn't know that the number is 10 to the 20, etc., he won't be able to work it out. It would take him years to calculate, and so that's a very safe code. But the person who knows, he can just plug it in and run it out for a few minutes, and he finds it. That's the basis of all security. So Archimedes was ahead of his time. He not only discovered pi, he discovered the way you manufacture secret codes. Actually, mathematicians and codes are well connected in history. One of my predecessors at Oxford was a civilian professor of geometry called Wallace, famous for his formula for pi, and he was very popular with both sides in the Civil War. And like Von Braun after the last war, every time the war changed, he was captured by the enemy and immediately put to work on doing codes the other way around. As a mathematician, he could survive the Civil War very comfortably. And I recommend that to you as a policy. If you want to survive difficult times, just remember to be a mathematician. Now, this picture here, I gave you a picture with one circle inside another circle, and you can imagine, I've chosen to draw it, so the circle inside is tangential to these triangles, and the one on the boundary goes through the vertices. Now, and I've drawn them here particularly in a sort of not symmetrical form. I've gone away from circles to ellipses, and these 2 ellipses are not meant to be in any particular connection to each other. They're meant to be more or less randomly drawn in the plane. And if you draw them carefully enough, like I've drawn them here, you will find that the there's a triangle whose vertices are on the outside one, which touches the one on the inside. But the great theorem discovered by the French engineer, Mr. Poncelet, by the way, in those days, most of the good mathematicians were engineers. They started life as engineers. Many, even modern times, started life as engineers. Then they realized that mathematics was more beautiful, and they drifted into mathematics. But almost every mathematician, until very recent times, started life as an engineer. And anyway, Poncelet discovered the beautiful theorem that if you have a triangle whose vertices are on one ellipse, and whose sides touch another ellipse, then wherever you start, you'll get the same picture. In other words, if there's one solution, there's infinitely many solutions. So with one triangle, you can keep drawing. Here I've just drawn two, but you can draw as many as you like. This is the famous theorem of Poncelet, which used to be taught to all geometers in schools in the days when they taught geometry. Unfortunately now, they don't teach geometry, they think it's a useless subject. But without geometry, we wouldn't have a lot of other things. And that picture of the two ellipses, you may think it looks very different from the two circles, but in fact, by elementary projective geometry, you can always move them so that the ones they have the common center and they're both circles, just by changing shapes. What's called projective geometry. So this theorem is the same as the theorem about circles. The theorem with symmetry is much more obvious, but you can distort the symmetry. It doesn't look so obvious. You get another theorem. Well, that's somehow a very important fact. You break the symmetry, and you still have a theorem. Now, we come to the really hard part, and here I probably have to go fast because I can't understand this myself. But if you ask what are the most famous theorems in mathematics, in the 19th century, it was the theorem of Abel and Galois. In the 20th century, it's the theorem of Kurt Gödel. Kurt Gödel was an Austrian logician, and he came up with a fantastic theorem which revolutionized the world. Everybody was totally overblown by it. His theorem has a very simple statement, but it's a deceptively simple statement. All simple statements are. And it says any mathematical statement you make, any theorem has to be formulated within some set of axioms. You give me the set of axioms, I write down the theorem. It says every time you do this, you will always write down a statement with the following properties. First, it actually is correct, but you can't prove it. But if you add some more axioms, then you can prove it. But actually, you've got to be very careful that the axioms you add are consistent. They don't lead to a contradiction. Because, as what Bertrand Russell said, I'll move ahead for a moment to Bertrand Russell. Bertrand Russell said that, and the fourth line down there, if 2 + 2 = 5, then I am the Pope. Bertrand Russell liked these kind of phrases. What he meant is if a statement is false, you can deduce anything from it. And so if you go back here, if a statement is false, adding that as an axiom would be disaster. So you must be sure that the axiom you add is consistent. And how do you show that something is consistent? Well, you exhibit something. You show that it exists. Here it is. So it couldn't have been impossible. And then the last stage is, even if you've shown that something is true, because you've proved it formally, usually when you've got to the end of a proof, you write QED, and you get your marks, you pass the exam. But sometimes people are fussier. They say, it's all very well to prove something is true, but how do you actually find it? Can you give me a construction? Now therein lies the story. There is the story. What is a constructive proof? A constructive proof is nowadays what we would call an effective algorithm. If you play with computers, as all those aged about 5 or 6 know, you can program a computer. And if it solves the problem after a finite number of steps, then you've got a useful algorithm. If the computer goes on and on for a very long time, it's not much use. So, and the definition of what an effective algorithm is quite a tricky one. But you all have a rough idea. This is Gödel's theorem. Now, the point about Gödel's theorem is it's always struck me as being so difficult, I couldn't understand it. I wasn't a logician. When I was a mathematician, I thought logic was the most useless subject there was, and I steered well clear of it. But preparing this talk, I realized that was a mistake. It's a mistake because, in fact, the example I've given you of the icosahedron and the dodecahedron illustrates that beautifully. Let us remember what we showed. We showed that, well, we told that there was no rule for colouring 5 things, so that you couldn't solve equations of degree 5, and so that was the difficult problem. But you could say that there is a solution to the equation of degree 5, but you didn't know how to do it. You couldn't prove it unless you went beyond trigonometry and you started to introduce these elliptic functions. Then you could show it. That's got to the first step. But that's only a formal proof. That doesn't explain why it works. Why it works, you'd have to get an algorithm for actually showing it. But that algorithm is exactly what you can't do unless you decode the system, because if you have a thing with a large, replace 4 by 5, large numbers, you don't know how to carry out that process, where to start. You can't decode it. So coding theory is just there. And if you can't solve a code, it's not effective. So that theorem I tried to indicate about the dodecahedron encodes all of Gödel's in a beautiful way. I always thought I could never understand it, but here I've explained it to 5-year-old children. And if you don't believe 5-year-old children are smart, go and try and play a computer game with your 5-year-old grandson, and you'll find out very quickly. So Gödel's theorem is beautifully illustrated by just a story about regular polygons. And regular polygons having more and more sides. The problem gets into the modern era, and with the modern era, we get all these beautiful results of cryptography. But it all goes back here, and Gödel's theorem is one of the most profound theorems in the history of mathematics. Not only mathematics, it has a major impact on mathematics, on logic, and on philosophy. You'll find no end of books describing problems of Gödel in terms of logic and philosophy. Every philosophy course taught about Gödel. Gödel was a genius. Unfortunately, he suffered from many of the problems that geniuses have, and eventually, well, I won't go into all the story, but at least one story I like to tell. I knew Gödel. He was a colleague at the Institute for Advanced Study where I was, and I sat next to him one time, and he talked to me, and he told me then the trouble with modern physicists is they don't try to explain, they just describe. And he knew what he was talking about because he'd written a paper with Einstein on general relativity. Gödel, the nice story about Gödel is that his friends, he lived in America for many years, his friends thought he should become a US citizen. So he said, all right. So then you do that, you've got to read about the US Constitution, go and appear before an attorney and swear to uphold the Constitution. Okay. So he went along and with his friend to the journey, and said, had you read the US Constitution? He said, yes, but I find it inconsistent. Friends said, keep quiet. Keep quiet. And I think he was probably right. Many judges at the Supreme Court had come to the same conclusion. First of all, I'm talking about biology. Remember, that's one of the titles of this lecture, biology. And so I want to say something about biology. I've learnt a lot by talking to biologists recently, and I think they may have learned a bit from me in return. I think there's a lot we can learn from the exchange between biologists and mathematicians. And I hope over this coming year we'll probably have some groups which will try to push that forward. There are a lot of remarkable mathematics behind biology, some of which is known to biologists, and some of which is not. The viruses which we came across, and the fact that they have shapes which are many icosahedral and often is a very important part. I should have realised it because many years ago, in 1959 or about, Aaron Krug got the Nobel Prize, and a friend of mine, and I got him to talk to mathematicians about the tobacco mosaic virus. But somehow it didn't stick, and I left it behind, and now I realise I should have taken it seriously, but the moment wasn't right for me, but it was right for the biologists. So they know all about icosahedron, and the early pioneers, Crick and Watson, knew very well about the relationship of the geometry to the viruses. One important property in biology that I learned, and it's coming to natural selection and Occam's razor, is that biology, evolution, tends to go for the simplest possible option, simplest possible successful option. So you can ask yourself, why are things come in pairs fundamentally? Why are there only 2 sexes instead of 5 sexes? Well, you can imagine life would be more complicated with 5 sexes. And because two, you need two in order to duplicate. You don't need more than two. Of course, you could try, and no doubt evolution has tried, and probably found they're not very successful. They don't last long. They probably died out. Not a single. So I think you can argue that evolution, natural selection, chooses the most successful option, the easiest one, which works and is easiest to do. And that I've written down Occam's razor. Occam's razor is the famous philosophical expression which says that you try to do the thing most economically with the cheapest possible structure. You don't go in for unnecessarily complicated hypotheses. If you do it as simply as possible, Occam's razor is the sharp end of logic. And evolution really agrees with that. I've got it down here, it says 2 win. In the battle for all numbers, 2 win over all the other ones. And it's a fundamental fact of biology. You just look around and you'll see it. And it's very, very prevalent everywhere. I mentioned again the Archimedes and the double helix, because I think it's so important it deserves repetition. But the thing I'd like to focus on at the moment is that the implications of this. Where does the human brain enter all this? Now, the human brain is, on the one hand, a product of evolution. Now, we've evolved, Homo sapiens has evolved through many versions to have a rather successful brain. And that brain then faces up to nature and has to try to... Well, first of all, it evolved so that it would be successful, evolutionary-wise. And therefore it had to fit in with the outside world. Had to relate to reality, otherwise it would not have survived. But the second question is, having got there, the brain can do more than solve the problem of the outside world. It can start to have its own internal life. And then the question is, now where is this taking place? Is it taking place is it inside the brain or is it outside the brain? So there are a lot of very difficult philosophical questions which like the interface. Where does the human brain fit in to understanding of the world outside? We are part of that evolution, and we're trying to study evolution. It's a very circular argument. There's a lot of traps there for the unwary, but you can't ignore it. I mean, evolution is there. Nobody disputes it. So evolution affects all science and philosophy, because you have to face up this whole question: how does the human mind evolve for evolutionary purposes? Address issues. Where does it fit in, and how does it happen? Now, I'm not saying it's an easy question, but I say you can't really understand human brain without looking at its evolutionary development, and then think of the implications. Well, and I will come to that later on with other consequences, but it's very important that we recognize the evolutionary consequences of the development of brains. Now, the second, so I'm talking now, I'm going to constructivism. Now, this is the area of mathematical logic closely related to Gödel, and we mentioned so on that slide, the importance of Gödel. Gödel's name is up there. It isn't, it's on my notes. All right. Now, the key, the big question at the beginning of the century, or for a while, was a big battle between David Hilbert, who was a great mathematician of the era, and other schools of thought. Hilbert wanted to lay down axioms for mathematics in which you could justify all that we normally did. And eventually Gödel showed that was impossible. The Gödel theorem showed Hilbert's program just could not work as envisaged. But on the other side, there was another famous character called Brouwer. And Brouwer was originally started off as an analyst who proves nice theorems about the existence of fixed points. But then he became a total renegade. He said, that's all nonsense. If I can't find a fixed point, what good is it showing it exists? So he believed in what's called constructivism. Only things that really mattered were the things you could actually construct. Construct didn't mean hand, but mentally. You had to have a method of producing something. And so there was a big battle between Brouwer and Hilbert, with Hermann Weyl, who was one of my great heroes, in between, trying to work out how you could develop foundations of mathematics and have the best of both worlds, satisfy the Brouwer's arguments, and yet end up with a nice theory. Well, the answer to that really is, I think, like this. I've gone through a similar process trying to understand this, talking to people and thinking about what Weyl did, what Hilbert did, what Brouwer did. I've ended up by being a supporter of Brower. Brower, if you like, was the extremist, fundamentalist. Brower believed there were only finite things, and things were finite, and infinity didn't exist. You talk about finite number of things, you ask a question, you ask for a finite number of steps, everything was finite. I asked you a question, you gave me an answer. I asked you another question, you gave me an answer. You only answered direct questions, you didn't try to go beyond that, you stayed within the realm of the finite, you were safe, because with finite things you can't get into trouble. But, of course, the finite number is as big as you want. It can go and get bigger and bigger and bigger, but at any given moment, only look in front of you. If you do that, you don't get into trouble. So this is his answer, and in a way it's a very satisfactory answer, and you dig down, you look at internal depths, only as far as you need to answer the questions that are being posed. You only are in a kind of courtroom. The lawyer asks you, did you beat your wife, or whatever it is, and you have to say yes or no. So basically, Brower says you only answer the question you're asked. Never any more. Don't try and write down general theory for all integers, for all this. Those are dangerous things to do. Don't do that. As long as you keep away from that, you are safe. Now, further down that line, I've got the word experiments. You see, this applies in a way this finance approach fits very well with what physics experiment is about. If you're a scientist, you never actually deal with anything other than finite things. You have a finite number of steps, finite number of questions, write down finite number of figures. You never actually deal with infinity. If you're a scientist, you're an experimentalist, everything you deal with is finite. In some cases, you may approximate by infinite things. You think there's so many of them I can't count. But that's only because you don't stick to the facts. If you're an experimental scientist, you must recognize you deal only with a world of finite things. So experimental science really is at the same level as Brower. It only believes in finite things. And that's very satisfactory. Very finite amount of data. A lot of ways there we're talking about data and how you get information nowadays. But the finiteness is always indeterminate. We don't know how far we want to dig until we start asking questions. We keep that in reserve. But on the other hand, this doesn't satisfy the mathematicians. Mathematicians want to go beyond finiteness in experiments. They want to go to an ideal world where things like infinity are allowed. So this is really where we get into the next level of discussion. But I'm emphasizing really that the constructivists are really like experimentalists. They really deal only with finite amounts of information. They may think they deal with it, but they only deal with a finite amount of information at a time. So Brower and experimental physicists should get on like a house on fire. Sometimes they don't, that's a matter of language. Now, let me go to the imagination. Now, this is very important. The word, it starts off, after all, we go back to Plato, idealism. When Plato, or before that, in the quintic genres, said a point is something that has position but no magnitude. They knew they were not dealing with real points. You can park a point with a crayon, or it always occupies a bit of space. You can't draw something which occupies a bit of space. The point doesn't exist as an object because it's too. They knew they were idealizations. And similarly, a circle doesn't really exist. You can draw a really good approximation to a circle. You can draw a circle with millions of stars from polygons. But it's not the real ideal circle, which has infinitely many edges, only exists in the ideal world of Plato. The Platonic world exists only in the mind. It's called the ideal world. And Platonists are people who believe in the existence of several worlds, the Platonic world, where these perfect things exist. That's been recognized all the time. People describe themselves either as Platonists or not Platonists. So the Platonic idealism is the world where things do not exist, but they're imagined. The imagination is where these things live, because it has to live somewhere. It doesn't live in the physical world. It's an idea. Where does an idea live? It lives in the mind of the person who has the idea. So inside the human mind, which I thought was more Platonic idealism, is where these things happen. And they are, of course, meant to be beautiful things. The circle is meant to be the most perfect object. Perfection is the hallmark of beauty, in this sense. The Platonic world consists of beautiful things. So there we have a relationship between mathematics and art. And so you heard it. Well, I'm sure that it cut out. I was told after my class, that's the sign. Then the human, in the human mind, imagination, we imagine things, and we imagine things by using pictures. Why do we use pictures? I mean, your mental state, if you see something beautiful, is, you admire perfection. What is it you're admiring? It's not outside in the world because it doesn't exist in the world. Only approximations exist. So where does it happen? Well, I think we have pictures around. I don't know what you do when you imagine things, but very often when you picture things, imagine things, you have mental pictures. That again relates to the way the brain's evolved. The brain evolved in order to deal with the outside world, evolutionary survival, and in the course of that, the brain will find it useful to have mental pictures. It could imagine things that weren't there. It could imagine what a tiger would look like if you met him around the corner. It could imagine things. So imagination was very important for evolutionary survival. And imagination is taken a state of matter, a state of mind. It is not directly related to the physical world, but it is in a sense outside it. Well, outside it really means inside the mind, because nowhere else the imagination can be, is inside the mind. So there are really different mental states, which I think one has to recognize, and the ideas of art and beauty and imagination of beautiful things, mathematics, they are part of the mental states, and they're not corresponding to physical states. They're idealization, they live somewhere else, and they live in the imagination. The imagination, as the word suggests, has to do with imaging. Well, imaging is the word we use, but again, think carefully. When you imagine something, you don't necessarily see an actual picture, you have some kind of blurred idea of what you've got. Imagination is much more looser and tentative. In fact, it comes before the actual concrete vision of seeing something more primitive. So I think these mental states which take place, certainly when I'm thinking mathematics, when you think about the creative part of mathematics, then that's long before it reaches any formal stage. You dream at night, you have some vision, you don't quite, if you try to grasp it, it disappears like all good ghosts. It's something which is intangible, and that's a mental state, which has to be recognized as having some kind of, well, I don't like to use the word reality, but some kind of existence, that only exists in the human mind, because the human mind is itself evolved to be a useful thing for dealing with the outside world. Again, you're getting back to the relationship between biology and evolution and the man. And I think at the end of the day, I get convinced that there are different mental states which are not just copies of physical states that represent the outside world, but in which, in these mental states, we have room for poetry, mysticism, visions, all of art. And so it is in this world here. It takes place inside the mind, which I've talked about, the imagination, and it has, of course, evolved by evolution, but it's not. We are quite familiar these days with science fiction writers who write about machines that have taken over the world and take charge of their masters, tell them what to do. Well, sometimes the human mind has gone through that process already. It's gone beyond its actual original function, which is to enable us to survive in the jungle and enable us to live in a world of our imagination and our beauty, which is a real world in the sense of experience, but is not represented by physical objects. So this is a world of the imagination. And I think there's no other way to describe it. that it lives in the imagination. The imagination is an entire world of its own, related to, but different from, the world of experience. So when we go back to Pythagoras, you remember that he was the person that Bertrand Russell said was the most important person who lived, because he saw the connection between numbers, mathematics, and the real world, and therefore he believed science was possible as a human activity. But he also, Bertrand Russell said, he was also be unwise, he didn't like his mysticism. Pythagoras had this mystical aspect as well. And I think, I'm on Pythagoras' side, I think it is true that the mind, there are states in the mind which are more to do with art and science together, beauty, and that is part of our experience. And to deny that is to deny a large part of our own human existence. Well, those are difficult topics. I need help from philosophers and logicians and so on to pursue the discussion. Let me go on to my next slide, because here I've written down mind. It's carrying on from the previous discussion in a way. I use the word mind to distinguish it from brain. Now, I don't want to get into technicality. I don't believe that the mind can exist without a brain. I mean, if I die tomorrow, I don't think my mind will survive. Although, it may survive in some sense. Ideas persist after the person is dead. So in that sense, you're a writer or a mathematician or a scientist, you are immortal. Your ideas will go on. But most of the time, your imagination stops with your death. But the fact that you have to exist in a body doesn't mean that you are only part of the physical part of that body. The imagination, the mind, is the part of includes both the physiological structure of the brain, but also has within it the capacity to imagine things that are not physical, that involve things like art and beauty and so on. So this is what I've written here is there's the external mind, and then there's the internal mind. And I've written down insight here. Insight is a word which is similar to imagination, means a way of appreciation of things which is not just the same as taking a camera picture or something. It digs more deeply into it. And now let's go back to the mathematical side. Infinity. Well, infinity is, as I said, doesn't exist in strict mathematical terms. You can approach infinity, you get bigger and bigger numbers, but you don't actually see infinity until you go into the ideal world. In the ideal world, then you do have infinity. You allow yourself to include infinity. People have captured infinity. In mathematical terms, you geometrically quite often add a point of infinity. Adding a point of infinity means we allow to use the symbol of infinity with suitable care, and it's been captured. It's been brought within our technical capacities. But that's an act of the imagination. Then infinity is not there by itself. We've added it to the things we want to talk about. We've brought it into our world as an ideal object. So the infinity is tamed by mathematicians in that way. They don't actually, it isn't there, but you capture it. And the advantage of that is mathematicians can know it both ways. One time they can say, well, we're only doing finite numbers, calculating, answering questions. On the other time, they can say, well, in our mind, in our imagination, we can go to infinity. In that world of infinity, we can do marvelous things. We can talk about complex numbers, doing all sorts of funny things which you are not allowed to do with finite numbers. So the beauty of mathematics is that it includes the skillful use of infinity. So that really doesn't take place in the physical world, it only takes place in the ideal world, in the planet. And that is living at the same time in a space where beauty is recognized. So they're not an accident. Beauty and platonic world go together, and that, when mathematicians discuss whether you're a Platonist or not, sometimes we're all Platonists. But we have to be careful to distinguish between what is the world of Plato and the world of Caesar. The imagination has its own life, and that life is shared with all the people in art and so on. Now let me come to the last bit here. I think this is a rather subtle notion, and I'd like to try to see if I can sell it to you. one of the things people say, they look at evolution of the cosmos. They say, well, and they say, what is the role of the observer, the scientist? Well, I think it can't be that the observer is important for physics of the world, but what happened before there were any people around? If you go back a few million years, even if you think dinosaurs had big brains, they weren't doing advanced mathematics. So, what was happening? How can you work out the relationship of the intelligence, understanding, to the universe when there was no intelligence? It looks like an insoluble problem. And then people appeal to God or whatever, like creation. But I'd like to tell you another idea, which is that, you see, the world of imagination is not constrained by the ordinary rules of time. I can imagine myself at the beginning of before the Big Bang, or after the Big Bang. I can imagine myself yesterday or tomorrow. Imagination is not constrained by time. You can travel, you can do time travel in the imaginative world. Nothing's stopping you. In fact, all the time we're doing that. When astronomers say what happened in the early universe, they're imagining themselves there. Or what's going to happen when we go to the end of the universe, they imagine it. So they're transporting themselves mentally by the imagination to a different period of time. Well, in that sense, imagination is time independent. It has the same properties people ascribe to God. If you believe in God, they are omnipresent. They're outside space and time. So, in that sense, the human imagination can envisage itself being in the early universe and seeing the early universe. In that sense, well, the early universe was being watched by people, even though people weren't there, because the people coming later can sort of imagine themselves back at the beginning. Ask, can you buy that one? Well, it's a better guess than most others. I think there's some truth in it. When you are in imagination, you're really independent of time. You don't live in the moment. You live anytime you want to. You're free to do time travel in your mind. All the science fiction we write about, we read about, where is it taking place? It's taking place in our mind because we can imagine ourselves in a different era, different time. And so there's nothing mysterious about saying we can imagine ourselves being in the early universe, even if there's nobody there. So the early universe knew that we were around, and by God, it had to behave properly. So, I mean, I think it's a better argument than most other arguments. I don't believe in the people who talk about, in the ordinary language of physics, people talk about the anthropic principle, why is the universe so constructed that we exist, all sorts of nonsense. I don't believe any of that nonsense. I think my argument is much better. And I think this is much more philosophically sound, it's closer to art, it's closer to our own experience, and it agrees with ideas of biology and computer science. This is the way the world really works. And I have to say that when people appeal to the great Immanuel Kant, the great philosopher, the greatest philosopher of all time, probably, and they appeal to him, and they say, well, what Kant have made of this? Well, the answer is, Kant, if he lived now, would have learned about modern science, and he would have updated his views, and he would have incorporated modern science into his philosophy, and he'd have been a smart aleck like everybody else. Imagine that Kant now would argue exactly as he was arguing in his time, is ridiculous. Kant was not stupid. He was using the science of the time. Science has moved on, there are more insights. He would have rewritten his philosophy, and I'm giving you my view of what Kant would have done. Well, my guess, he isn't here to help me, but I think Kant, updated by modern science, is much closer to what we really have. Of course, these problems are difficult. There's debate, plenty of room for debate by philosophers and so on. But I think these are better guesses than you get by using the conventional treatments. Now, I think I'm going to end now because there's a little short video to follow, which is only a lot of quotations and sort of comments, which are like relief from all this difficult stuff that I've been giving you. Then there'll be time to have a few questions where you can shoot me down again. Now, we've gone on, I just kept by going back to the slide I showed before about Pythagoras. Now, look at the line at the bottom. This is the picture of Pythagoras and Bertrand Russell. Bertrand Russell said Pythagoras was intellectually one of the most important men that ever lived, both when he was wise and when he was unwise. He liked the sting in the tail. And now, let me explain what he meant by the first bit. Why did he say that? Well, Pythagoras, whose dates are there, lived 2,500 years ago. He made two fundamental observations, not necessarily discoveries, but he was the first person to realize its significance. First was to do with music. Now, I'm not a musician, but I'm told by my friends who are that there's something called the perfect fifths, something called the octave, and the numbers are such that 3 over 2 to the power 12 is extremely close to 2 to the 7th, but not quite. There's a very, very small error. If you've got perfect pitch, and if I ask, put hands up, there must be 1 or 2 here, perfect pitch, you can tell the difference. Otherwise, I'm tone deaf, I couldn't possibly tell the difference. But this was Pythagoras realized the importance of this. Second thing he realized was, of course, the famous theorem of Pythagoras, which is not due to Pythagoras at all, but much older. And Pythagoras noted not just that there was a theorem that says if you have a right-angled triangle, the sum of the squares equals 50, that he realized that it had integer solutions, 3, 4, and 5. Now, to realize the significance of that, remember that if you replace 2 by any number bigger than or equal to 3, Fermat's last theorem, proved a few years ago by Andrew Wiles, said there are no solutions. So there was enormous difference between 2 and other values of n. And that was Pythagoras putting his finger on a very important point. And so what he came to the conclusion was that music and geometry, which are the two most important things in primitive old cultures, were based on mathematics. And then he said, we don't need to appeal to unknown gods who do mysterious things, jump around. We just appeal to mathematics. Mathematics is at the root of knowledge, and that thereby began the beginning of science. The world was ruled not by gods, but by logic. But there were laws to be discovered. Science was born with Pythagoras. That's what Bertrand Russell meant when he said that he was wise. When he said he was unwise, he really meant that Pythagoras was also a bit of a mystic. And Bertrand Russell didn't like mysticism. And actually, I think on this occasion, I side with Pythagoras. I think a little bit of mysticism is very important in all forms of life, imagination, and so on. So I am a mystic like Pythagoras. Now, let me end with a few quotations. Well, this one is a quick one, appropriately with the name Jonathan Swift. And it says, I'll read it to you quickly. So naturalists observe, a flea has smaller fleas that on him prey. And these have smaller still to bite them, and so proceed ad infinitum. Well. Going ad infinitum is a very important mathematical observation, and the bit about fleas, well, it's a bit of literary embellishment. Now let me go back to the icosahedron very quickly. Here is the icosahedron as drawn by Kepler, in his famous book. Now the famous people associated with the icosahedron I've named up there. Well, you recognize many of them. Pythagoras. Plato was the most important disciple of Pythagoras. Leonardo, Michelangelo were, of course, great sculptors, architects, men of all types. Kepler was the man who believed this and believed many other things. And then the next line, you may not know that they're there, are the famous biologists. Crick and Watson, I'm sure you've heard of. Wilkins and Franklin worked simultaneously and would all have got the Nobel Prize together, but unfortunately Rosalind Franklin died. And Caspar and Klug came later. They were the ones who showed that the DNA virus is basically icosahedral. Then there was Buckminster Fuller. Buckminster Fuller was an architect. He designed these geodesic domes. He was a very interesting man. He held a US patent for his geodesic dome in 1945, and then after that he influenced greatly Harry Kroto, who discovered carbon C60 and named it after him. They're all called fullerenes. So there's a lot of history in the icosahedron, which I've just given you a very quick thumb sketch on, because I've noticed my time is coming very fast to the end, so I speed up here. Few quotations. You can read them for yourself. Pythagoras, numbers rule the universe. Plato, God is a geometer. You all agree. Newton, God created everything by numbers. Modern quotations, we have two here. one by Karl Weierstrass, who was the symbol of hard, rigorous analysis in the 19th century, but he had a soft spot. And he said it is not possible to be a complete mathematician without having the soul of a poet. And Hardy, over there, said beauty is the first test of there is no permanent place in the world for ugly mathematics. Then we move on to physics, mathematics. Two famous, Albert Einstein and Paul Dirac. Einstein is an old man, Dirac is a young man. Einstein said, the most incomprehensible thing about the world is that it is comprehensible. Einstein was the master of sound bites. He was always bothered by the press. He had a nice line for them all. Dirac was a man of few words. He just said, a physical law must possess mathematical beauty. And finally, I'll come to my great hero, Hermann Weyl, and I call this artistic truth. Weyl made many beautiful sound bites. My work has always tried to unite the true with the beautiful. When I had to choose one or the other, I always chose the beautiful. And then another one, I believe there is in mathematics, in contrast to the experimental sciences, a character which is nearer to that of free creative art. And Weyl was a great stylist. His writing is absolutely beautiful. Russell, even strict Russell, said mathematics possesses not only truth, but supreme beauty. Now, I've passed to the last slide, essentially, youth. There are young people here in the audience, and there are old people. I am in the latter category. And Hardy said, no mathematician should ever allow himself to forget that mathematics, more than any other art or science, is a young man's game. Oh dear. Underneath, you see a picture of a young man. He was a young mathematician, logician, better known as Lewis Carroll. And here is a quote by him about old age. And I'll read it to you. You are old, Father William, the young man said, and your hair has become very white, yet you incessantly stand on your head. Do you think at your age it is right? In my youth, Father William replied to his son, I feared it might injure the brain. But now that I am perfectly sure I have none, why, I do it again and again. Thank you.
Okay, thank you very much, Sir Michael. So we check the time. So we do have some extra time for questions in the assembly. So I will repeat your question. So please. Yes, again, first.
People often comment on the idea of the unreasonable effectiveness of mathematics. Do you think there's any hope of arriving at an understanding of why and how mathematics and the world of the imagination and things that don't physically exist should be so successful in explaining things that physically do exist?
Right.
Can you repeat the question?
I will try to repeat the question. So mathematics in itself is an abstract science, is it? And therefore we are using it to try to explain.
No, not with the answer. Just repeat.
So I saw the mathematics could be used as a tool to explain the whole world. Is that your question?
Yeah. I think I understand the question. And it's well known there is a famous phrase about the unreasonable effectiveness of mathematics made by a figure. What he meant was that mathematics seems to do much more than you think it should do. It answers questions you haven't even asked. It's somehow one step ahead always. And that is true, and I think it's I think I've been trying to say that it's very closely related to, of course, the nature of the way our brain works, our mind works, we can distinguish between the two, and we've evolved through evolution. And the way I try to explain, go back to Pythagoras, mathematics is the root of all things. So of course, if it's the root of all things, it has to come back again. So it's not a surprise that mathematics is so effective. If you look into its history, its evolution, and the background, it's almost inevitable. I think I was trying to sell that argument. So, and that goes beyond its utility in the world of actual physical sciences into the world of the imagination, because, well, I mean, they're a bit more delicate, because this mathematician in his role as a Platonist who affects the imagination, not the mathematician in his role as an engineer. And he isn't just turning nuts and bolts. He is thinking. He is imagining. He's talking about infinity. In that world, he's living in the world of imagination. So it doesn't. These questions, of course, have no simple answers. But I think these are great topics to discuss and talk about, and they will never go away. But I think recognising the significance of mathematics across a wide spectrum of activities, including the imagination, is, in some sense, a sort of explanation of this question, yes.
Okay, we have a second question here, so I think it would be wise for me to come forward to you.
To sort of press the point a little further, part of the whole issue with Gödel and Hilbert and Brouwer was about the reliability of mathematics. If mathematics is something of the imagination, how is it that when you prove a theorem, somebody else accepts it? And the argument was about the reliability of judgments about these infinite sets and the fact that what does it mean to say there exists something without actually producing it? So reductio ad absurdum, to show that there must exist something, didn't work. So do you think that that's explained by evolution and by the fact that we share a common mathematics? Do you think that if there were aliens, they'd have a different mathematics, or when machines take over the world, they'll create mathematics we couldn't create? Or is there something intrinsic about the mathematics?
Well, those are very difficult questions. I think I partly agree that it's the fact that we share a lot of things because we've evolved in evolution together that these things are possible. What happens if you had totally different aliens and built totally different models? I think it's a difficult question to answer. In some sense, we wait and see whether there are people on exoplanets or not. So, what you might say, an open question. And if they are, what sort of structure they would have, and whether they would think in the same ways. I think the question, going back to the question of logic and compatibility, I think the development of very complicated mathematical structures which justify the continuum and all that sort of story, it is a long process, which is you start off with these finite things, then you sort of combine that with the imagination and dealing with the infinite in a way that is very tricky to put together, and that, nobody denies that. All the difficult questions that logicians struggle with are there, but I think we can sort of tackle them a bit more better together than we did in the past, partly recognising the way that human minds evolved, taking account of biology as well, and but it's an ongoing discussion. I mean, these are things we will not get to the end of this. I'm happy we will carry on this discussion in the informatics forum with all the clever chaps who work there. I don't have all the answers, but this is the beginning of an approach. If you have a better foundation on which to rest, you're happier state to carry forward the arguments.
Okay, thank you. I will take an extra question from the back here.
You've spoken about imagination. Imagination exists in the mind. I'd like you to make some comment on the distinction between public and private. The imagination, if it's restricted to the private, can lead one off into all sorts of fantastical places. And I wonder if you think that public discourse imposes some kind of useful restriction on private imaginations.
Okay, so a question about imagination, the private versus the public imagination.
Right, well, I mean, obviously, if you're talking about poets or musicians, they create things in their own imagination. They're not dependent on the public discourse outside, maybe get a stimulus. They create their own things and they put them on the table for the public to discuss. So there is a role, of course, for public discourse, examination of new ideas, but there's a big lap, both in space and time. It may take a long time for an artist's work to be appreciated. It may have to revolutionize people's thoughts, expectations, the purpose of, the function of artists in general is in fact to stimulate new ideas. They bring their own internal thoughts onto the table and try to affect the views of the public discourse. And the public discourse is, in some sense, both a receptacle and a critique. And it will respond to that. Over time, hopefully, take the better ideas, build them into its structure. There'll be a long time lag between the creation from the individual and its recognition and absorption by the public debate. But that is part of the process, but then you have to have both. Obviously, an artist who does things that nobody ever appreciates is wasting his time in some sense, or at least you may have to wait thousands of years. So normally you'd expect the private dimension to have an impact within, but that might take a long time. Some artists' work, or musicians' work, or painters' work, maybe wait for 50 years or 100 years. So there is a time lag, but that time lag is not wasted because people discuss, interact, reform. So I think it's a very interesting arena. But they both have to be both important.
Okay, thank you. I think we are now reaching the time. Yeah, it's 12:45. So thank you, all of you, for attending this first two lectures this morning. So this morning was a launch for a series of lectures that will span over the next 6 months. So the aim of this lecture to present the world views envisaged by Einstein and Dirac. And the next series of lecture will have invited speakers from different countries and different fields, including chemistry, biology, cosmology, computing and philosophy. So just as today's lecture, they will be aimed at non-specialist audience, and so remember that all will be welcome. So thank you again, and thank you the technical staff of the university for helping with this lecture today. So I believe they all deserve a round of applause from us.